Welcome everyone, I'm Daniel Munoz from the Universidad de Málaga, and this is a paper of the SPLC conference in Graz, Austria, in the industrial track. As the title mentions, it's about optimizing virtual network functions based on quality measurements. This work is motivated by the needs of a European H2020 funded project that Universidad Málaga belongs to, called DEMON, acronym of Network Intelligence for Adaptive and Self-Learning Mobile Networks. And in summary, it sets in the Industry 4.0, where it designs an end-to-end network intelligence native architecture for beyond 5G, let's say 6G, to fully coordinate network intelligent assistant functions. The consortium of the DEMON project has academic partners and industrial partners. In this case, the industrial ones are Telefónica, Nokia, and SRS mainly. Part of the problem that we are tackling with DEMON is the softwarisation of network functionality within the network itself. That means that we are seeing the networks as general purpose platforms. Then the functions abstract from the specifics of the hardware, getting rid of the heterogeneity. Where do we find this? On the Industry 4.0, that it extends to automation, big data, cloud computing, IoT, etc. Everything is digitalized in a smart way. What we find? Configurable services with embedded quality of service. That means with quality requirements within the network. How? With a smart and proactive orchestration and our deployment. That means we try to optimize where we or how we orchestrate and where we deploy the virtual network functions. Where do we find the product line here? When we customize the services with a variable dynamically quality of service. There are complex requirements, like for example reducing cost, energy consumption, and latency in a trade-off. Unfortunately, in DEMON, we don't only have Boolean characteristics. There we present a regular feature model with three features, a root, A, and the childs B and C, with a NOR relationship. But we need to extend it with first numerical features and arithmetic constraints. Also with feature-wise quality attributes, with simple aggregation functions, for example the cost and the addition of the costs to calculate the quality attribute value of the product. Variant-wise quality attributes, they are so complex that we cannot generate a proper aggregation function. Then they need to be identified by products, related to products and not to features. Then we need to add complex constraints that involve both types of quality attributes at the same time. Just an example, multiplying the cost 2 times should be less than the latency and the energy added. We need customizable reasoning. For example, with a weighted multi-objective optimization function, where 70% will be the cost, 30% will be important the energy rate. And how do we calculate that new domain, the energy rate? By dividing the energy of the latency, energy by time. Is there any tool that supports all those extensions? As we can see summarized in this table, unfortunately not. Although the categorical framework from category theory allows a flexibility to program feature level quality attributes, configuration level quality attributes, and aggregation functions for different optimal search operations. We're going to briefly introduce the categorical model. First of all, categories are formed by objects and arrows, that's all. We can see there on the left side an extended feature model, the corresponding quality model, and the corresponding quality aware space. On the right side, we can see an instantiated category. The structure of the category, more similar to a meta model, is defined in the schema. There we can see the objects of the category, the features, the feature level qualities, the configurations that are a set of features, the qualities, the configuration level qualities, that is a set of qualities, and the binary relationship between configuration and configuration level and sets of configuration level qualities. Once we define that structure, then we need to add the instances. That has a domain, for example, Boolean domain, string domain for the names, etc. Features, they have a name besides the value, for example, manager, main, gateway, as well as the attributes. For a more detailed explanation of the category for software product lines, we refer our previous work in Casey. But keep in mind, the object features of the category is FS. The acronym for the configuration one is CC, from complete configurations, quality attributes for the set of configuration level qualities, and QMC for the quality measured configurations for the binary relationship. Here, as an example, we present a graphical representation of an instantiated software product line category. That's called an outlook. Here is a reduced version of a model from Daemon, the project Daemon, called Virtual Network System, VNFs, and it's a reduced version, and we can see how the center element, the center feature, is the root, and then we define different features and different qualities. Also, feature level qualities like dependability, usability, and security that are linked with features. And then we have the cross-true constraints, even arithmetic cross-true constraints, and in the low right, it summarizes the binary relationship that will be arrows between leaps forming a complete configuration and a time and an energy values. Having clarified the categorical modeling, we move forward to the reasoning. For that, we present what we are developing, a framework for the state-of-the-art categorical reasoner, CQL IDE. First, we need to start with the meta model. This case is the categorical software product line schema. In there, we have objects, domain, and arrows. That's all. We define features, we define hierarchical and cross-tree constraint relationships. And they are the type Boolean, the simplest. Once we have the structure, we can create instances, we can create models. In this case, a feature model with 3 features, A, B, and C, and an OR relationship. Now, the software product line expert can, through CQL IDE, through the framework, add constraints and user requirements, and also request a reasoner operation. In this case, we'll be counting the quality attribute space size. We need to define in the categorical reasoner the result category. That means the structure of the results. In this case, it's a simple object with a simple element of type integer. That will be the number of the size of the space. In this case, it's 15 because we have 3 products, A, B, A, C, A, B, C. For 5 quality attributes, we are considering the same quality attributes and in the BNS outlook presented in the previous slide. We have usability, extendability, and so on. Having defined the reasoning framework, we now move on to how to declare the reasoning algorithms. CQL IDE works with functional programming based on lambda functions. Here we present the report algorithm, where we first calculate the number of Boolean features. That means the attribute numerically set to 0. Likewise, for the numerical one, we check that the attribute is set to 1. For the logic and arithmetic constraints, they are differentiated by the operators they are using. To check the number of to count the number of configurations, that's a pure model counting. We just count that complete configurations relationships exists and how many of them, regardless of which features are involved in them. To check the measured quality attributes, we just check from those which one has an attribute, whether it's from the binary relationship or from the feature attribute. In 7, we just obtain all the data from the quality attributes at the feature level, the name, the value, and the domain, regardless of which features they are linked on, and so on. And likewise, for the complete configuration level ones, we check the QAS object and subtract the name, value, and domain of them. With algorithm 1, we generate the data necessary to fill this table. Also, in this table, we present the software product lines that we use to evaluate this work. They are ordered by the configuration space size, with the exception of VNS, the reduced version of VNS that is presented alongside the full version. We can see how it is an assorted product lines with different features, different numerical features, different quality attributes at different level, and different number of quality attributes. Our objective with the 5 product lines is to test them for different state-of-the-art reasoners and compare their scalability and support with the categorical reasoner. Here we summarize the operations for the report. Where we find an asterisk, it means the solver ignored the quality attributes. And that's a partial support of the operation, and then when unsupported, it's a complete unsupport of the operation. We can see how Clapper is the slowest, but still it's at reasonable times. The fastest is the Python framework, but it's mostly not considering quality attributes because it doesn't support quality attributes at all. Then that could be a reason for its speed. On the other hand, the categorical reasoner is almost as fast as Python framework and supports everything. In algorithm 2, we can check the aggregation of individual features to a value of the complete configuration. The lambda function is straight ahead. We perform the aggregate function over the different features composing a complete configuration. In this second table, we replace the Python framework by one supporting quality attributes for the aggregation. In this case, Satibea, which is more a machine learning predictive reasoner. Here the asterisk means that the aggregation operation is replaced by addition. So for example, if it would be a multiplication aggregation, it is replaced by addition because it doesn't support other aggregations further than addition. The operations are unconstrained, so we generate the configurations with the complete configurations with the aggregated value. The constraint means we are constraining the complete configuration generated value. For example, I want just configurations with that cost less than 5 euros, the whole configuration, and the range likewise, but between 2 and 5 euros, for example. Again, we can see how Clapper is the slowest, but yet with reasonable times. We can see how the categorical reasoner is first the fastest for slow model for small models, but once the model gets increasing, when the search space is increased, it tends to go similar to Claffer, but yet supporting every operation, every aggregation. Then Sativea is a much learning one. And then because of the predictiveness for small and large models, the timings are similar. We are not discussing the accuracy. Algorithm 3 is simply searching for optimal products. And the lambda function, first we need to compose an aggregation to convert quality attributes at the feature level to the configuration level, and then we apply an objective function. In this case, we keep with the same reasoners, and the operations is minimize and maximize the quality attributes. The multi-objectives, it's keeping a kind of trade-off. The weighted is a trade-off with different weights for the different quality attributes. And the new domain, it includes, like in the example in one of the first slides, creating a domain based on other two quality attributes domain, like watts parting from joules divided by seconds, like the energy rate. In this case, we can see how Claffer and Sativea almost doesn't support advanced optimizations, just the basic ones. And even though the configuration level quality attributes are ignored because they just support feature level quality attributes. Regarding timings, similar to the previous one, Claffer tend to be the slowest. The categorical reasoner tends to be in between, getting slow for large model, but not as slow as Claffer. And Sativea, as it's a predictive one, doesn't care so much if the space size is small or is large, because the number of samples is the same. Then more or less the timings are equal. Again, we are not discussing the accuracy of that optimization search. Finally, we can discuss the research questions. Which is the level of empirical support that the state-of-the-art currently has to represent and provide reasoning to quality measure virtual network functions? Well, it could be viable in Industry 4.0 if it is extended like our categorical ID framework for SPLs. Nevertheless, it's not as easy to extend as a configurable and flexible language like categorical reasoning. Is our framework for product lines feasible alternative to analyze and optimize virtual network functions orchestration? We prove that extended SQL IDE for the quality-aware operations provides support for managing the quality of service in virtual network functions orchestration. How do the alternative tools scale for the complete set of quality-aware reasoning operations present in software distributed network systems? Well, all the solutions scale nearly for the assorted product lines, quality attributes, and reasoning. That's what we've seen with the RAM times. To wrap up, we present some conclusions and future work. First, we reflected on the table comparing the different state-of-the-arts. The first one, there is a lack of understanding of methods and tools designed explicitly for advanced quality-aware analysis and optimization. Most of them just supported Boolean features and simple reasoning. Our categorical framework successfully tackled the expected quality-aware reasoning in network softwarisation based on 5 different real-world SPLs, presented in a table, with several quality attributes, a diverse of them, and up to 20 different operations. While the state-of-the-art scale linearly for the operations that they support, some tools were faster than others just in specific operations, like for example, the Python framework because it doesn't consider quality attributes, or Sativea for large models because it's doing prediction and the number of samples were the same. As a future work, we should extend the evaluation by including larger spaces, optimization accuracy discussion, and also accuracy and resonant time trade-offs discussion. We should extend the categorical framework with sampling and learning support, and also test other categorical tools and provide graphical interfaces. I thank the following funded projects that allowed me to be here. And that was all. Dankeschön.